So might as well start away. So thanks for everyone coming along to this night's event run by the GB Region of Engineers Ireland. To anyone who's unfamiliar with Engineers Ireland, we are the regulatory body for engineers in Ireland. We have about 20 to 25,000 members. And the GB region, we represent all of the UK. And we've got a very exciting technical talk tonight done by John McLoughlin of ESB International. So it's not just in Ireland, ESB are around the world. So this is one of their flagship international projects. John is going to talk about it shortly. Just go through the basic health and safety stuff. No fire drills planned tonight, but the main fire exits are out the way you came in. So stay safe is the main thing. And we also have our presidential address on tonight in Dublin, where our new president will also be giving a similar talk on Ireland's energy needs. So that'll be up on our YouTube channel next week. So watch out for that, and we'll send the link around to the members and put it up on our Twitter websites. And we're quite a sociable group as well. So after a talk and Q&A tonight, we'll be going to the Prince William Henry pub for a few refreshments. So that's well earned. And I'm serious on we are. And so it's the Prince William Henry, it's just out the door, turn right, and it's just 100 meters down the street. But no doubt we'll delegate someone to lead the group out. So I'll start off with John, if you want to begin.
Thank you very much, Hugh. Thank you. Good evening, ladies and gentlemen. First of all, I'm going to start off by playing a short video of the finished product at Carrington. We've just completed the construction of the plant and is now in commercial operation. And recently we did some drone video footage of the plant. So just to give you an idea of what the finished product looks like, I'll play this for you. Okay, I hope that gives you a bit of an idea of the scale of the project. And what I'm going to do now is go through a number of different aspects, some of the successes, some of the challenges that we had, and some of the key facts and figures about the project. As you said, my name is John McLoughlin. I'm a chartered engineer chartered member of Engineers Ireland, and I graduated from Civil, Structural and Environmental Engineering in Trinity College in 1999. Since then, I've been employed by ESB International, so I've only had one job in my professional career, and my latest role is as site manager for the ESBI team in Carrington. So what I'm going to do is I'm going to go through different aspects of the project, and I'll start off with some project key statistics. It's a £700 million investment. It's the largest investment that ESB have currently undertaken. The plant generates 884 megawatts of electricity, which is equivalent to enough electricity to provide power for 1 million homes and businesses within the UK. Based on this evening's electricity grid, the current demand is about 38,000 megawatts on the grid this evening, and Carrington is operating at base load, providing 884 megawatts. So we're providing about just under 2.4% of the demand on the grid this evening in the UK. It's a combined cycle in that it reuses the exhaust from the gas turbine to power the steam turbine. And I'll go into a bit more detail later on that. We've worked just over 4.9 million hours on the site to construct the plant, and at the peak we had 1,000 workers. There was a 10-year development period to get the plant from an idea in someone's mind to a commercial plant we have today. And we commenced commercial operation on the 18th of September. So 11 days ago, the plant went live. And it's the largest single gas generation plant within the ESB asset fleet. ESB's largest plant is Moneypoint in Clare, which is just a bit larger at 915 megawatts. That's a coal plant. This is obviously a new generation gas. That's just a timeline there, just showing the duration of the development of the project from business development back in 2007 and 8, right through the development phase where we picked the site, we bought Carrington and carried out the enabling works, got the contracts in place, got all the financing sorted out, and then started construction in early 2013, and then up until September this year when we went commercial. I just want to go back previously to the 1950s. The site that we built on was the site of the old Carrington Coal Power Station, and there's a photograph of the coal plant there. That was a 240 megawatt plant. So it was the plant we have now is nearly 4 times the size of the old coal plant. And in terms of the efficiency of a coal generator, it had an efficiency of about 33%. Efficiency is what we talk about, how much energy you can extract from the raw material that you're burning. So from the coal, you can typically get about 33%, and from the natural gas, our plant can get about 58%. So we've got about 4 times more output, twice the efficiency, and we're using up a smaller footprint that the original plant would have used in the past. I've just got a few more photographs of the old plant. That's inside the turbine hall during the construction time. You can see a lot of activity taking place there. It's a busy area. And then there's a picture there of a few guys installing some sheet piles. I think we're all happy to see that health and safety has improved a lot since the 1950s. They wouldn't be allowed to be doing what they're doing there in that picture these days, thankfully. Also, just out of interest, the old plant was it was a state of the art at the time, and it got visitors from all around the world to see it. And we have a copy of the old visitor book from the plant, and you'll see there the first 4 names. They're senior government officials from Russia. And you can see CCCP Moscow on their address line there. People came from all around the world to see the old plant. I don't think we'll have anybody from Moscow visiting for this plant, maybe. Just put Carrington in context with the UK grid. The maximum demand in the UK is approximately 52 gigawatt hours, and that's a moment in time. That's for a 1-hour period. Obviously, demand goes up and down with the seasons, the weather, the time of the day when everybody's at home cooking and factories are still open. The maximum demand is normally around middle of January when you've got the shortest days and the coldest weather. So at the moment, demand is about 38 gigawatts, and it's steadily going up over the next few months, up to 52 in January. The existing coal plants in the UK are currently being closed down. They're big generators of carbon, and they're less efficient than other generation types, including gas plants. So they're all going to be shut down in the next few years. And also, as everybody's aware, there's a major increase in sustainable energy production all around the world and in the UK, and most of this is coming from wind energy. Just show the main breakdown here of the main sources of energy production in the UK. You've got 30% from gas, 24% from renewables, 22% from coal, 21% from nuclear, and then 3% from others. The others would account for interconnectors across to Ireland and across to mainland Europe as well. The one thing to remember there is that in terms of the coal, that 22% is going to disappear. So something else has to fill the gap that 22% leaves behind. And then the renewables, because most of the renewables are from wind, the wind doesn't always blow. So on days when the wind's not blowing, you need a backup of another kind of power to provide energy on that given day. In terms of availability, a gas plant like Carrington would have an availability of up around 90–95% of the time it's available to supply electricity. According to the National Grid website, wind energy has an availability of around 22%, so you can see the difference there. That graph there, there's quite a lot of information on that graph, but I think it just shows the movement of energy production in the next few years. This was prepared in 2012, but the general theme still holds. Where you can see at the bottom, the dark brown shows the coal and the oil tapering off and disappearing by 2030, and you can see the large increase in the renewables, which currently stands at 26% in 2016, up to 36% in 2024. And then you have the nuclear, which is getting larger again from 2020, and that's because of the investment that is being made at the moment in a number of new nuclear plants in the UK. The first one, which we're all aware of, being Hinkley Point in southern England here. Though from 2012 to today, the development of Hinkley Point has probably been delayed a bit, so the point in which that comes on the grid may be a few years later. Overall, based on the reduction in coal, the increase in renewables that are not always available, and the possible delay in nuclear, there's an opportunity there for Carrington to fill the gap for the next few years. Before construction started, this is a photograph of the plant the site that ESB bought in 2008. The old power station we saw earlier had been knocked down to the ground and taken away. All the foundations and everything below ground had remained. So the first job that ESBI did when we went in there was to remove all the old foundations and uncover the old piles from the old power station. When we started digging, we realized that there was 5,500 piles under the ground, and there was just a maze of these piles throughout the entire site. So that's a photograph there that we sometimes call it the Carrington Terracotta Army. And in order to manage this situation, we couldn't remove all these piles because of the depth of them. So what was decided was we cut them all down 4 meters below ground level, and then we do precise surveying of the exact location of each of the piles, their exact diameter and their verticality, because not all the piles are vertical, some of them were at angles. And with all that data then gathered, we were able to give that to our EPC contractors, so that when they designed their piling solution for the new power plant, they were able to thread their piles in the gaps between the old piles and the ground. So we had a situation of 5,500 old piles in the ground, and we've added 3,000 new ones between the old ones on site there now. Some statistics for you, more numbers. In total, we've worked 5.5 million hours on all the projects to bring this plant to fruition. That includes projects for the gas pipeline supply to the plant, and works with National Grid for the electrical connection. As I've just said, we've installed just over 3,000 CFA piles on the plant, and we poured about 35,000 cubic meters of concrete. During our time there, the ESBI team has carried out 2,700 quality walk downs to ensure that the contractor is providing what ESB has paid for, and and that the plant does exactly what it needs to do. And then during the commissioning stage, we witnessed 1,800 witness points to ensure that the plant does actually do what it's supposed to do. 17,000 punch list items were addressed. That is a high number, but it's a high number that has been closed out in the entirety of the project. And both gas turbines, we have 2 gas turbines on site. They both have the equivalent operating hours of less than 3,100 hours up to today, up to the moment of commercial operation. It's like when you buy a car. If you want to buy a brand new car, you don't want thousands of miles on the clock already, because it means you'll have to maintain or do some work on the car sooner. So the lower the number of hours you have on the car, the better for you. The lower the number of hours on the gas turbine, the better for our operations as well. The norm would be around 3,500 EOH, and we're delighted to get it below that. We carried out 60 days of reliability runs to prove the plant before we took it over. That included 2 30-day tests for each of our units, and they included a number of different start scenarios. We've got there 16 hot starts, 32 warm starts, and 2 cold starts. Again, like the analogy of a car, if you're buying a car, you could take it on a drive 10 miles down a nice smooth motorway on flat ground, and it goes no problem. But maybe you want to drive it up a mountain, drive it in different conditions and see that it actually works as you want it to. And by starting the plant in different scenarios throughout the reliability run, we were able to stress the system and see that it does what it's supposed to do. And we have equipment supplied from all over the world. I tried to put a pin on a map of different countries. Most of the major equipment has come from the big manufacturers in Europe, and some of the other far-flung places where we've taken equipment. We had a generator made in China, and our boilers were made in Singapore. The Manchester Ship Canal runs past the edge of the site. This is a Victorian waterway, and we utilise this waterway for bringing the heavy loads into the plant. This allowed us to remove any congestion or disturbance to the local community around the plant, and we brought about 50 of these large items in by barge. That photograph there is showing one of the gas turbines being unloaded from the barge at our temporary barge landing area at the plant. Because we had the luxury of using this facility, we were able to bring larger items than could actually be brought by road in the UK. Generally, the limiting factor for deliveries on UK roads would be the clearance heights of motorway bridges. So we were able to bring items of a much larger scale that could be pre-manufactured in a factory with better quality control elsewhere, brought in by ship into Ellesmere Port, put onto a barge, and brought up the ship canal to the plant within a matter of hours. That's just another photograph there of the barge reversing into position at the plant. Internally within ESB, we won an Environmental Impact Award in 2014 for the innovative use of the ship canal for this purpose. And we were also shortlisted for a Corporate Social Responsibility Award in the UK in 2014 as well. And this was quite a prestigious nomination for us to receive. Incidentally, the barge that we use, there it is transporting Concorde very close to where we are at the moment. Robert Wynne and Sons have built this ship that is able to navigate the UK waterways like the Manchester Ship Canal, and is used for many purposes, as you can see there. In order to supply gas to the plant, we had to construct a 2.5 kilometre gas pipeline from the national grid transmission network close to the plant. Most of that pipeline route was a direct cut and open trench excavation works, though about 1.1 kilometers was a horizontal directional drill. On the left-hand side there's a photograph of the drill rig at the launch pit, where the drilling takes place from, and at the bottom photograph is the drill bit that was used for drilling the hole. The photograph on the right just shows the gas pipeline ready to be pulled into the tunnel once it was ready for receiving the pipe. In general, the principle of drilling completing a HDD is that you start on the left-hand side there where the rig is, and you drill your tunnel. You direct underneath any obstacles. You find your good stratum. In our case, we had sandstone rock down about 20 meters down. We get into the sandstone rock, and we come out again at the receiving end, which in our case was the power plant. And then you go backwards and forwards a number of times to ream the tunnel, to make it larger, to get it to the right size that you need for the pipe that you need to install. And all throughout that process, you're injecting bentonite mud into the tunnel to ensure that the walls of it do not fall in. In our situation, we had a problem at the very start of the works, where we're at the launch pit, and you've got the red line there, which is the direction of where the drill would go, and then either side of that you've got two black lines there, which would be a casing, which is basically a steel tube about 1.1 meters diameter and about 20 meters long, and that's to get you through poor ground. For the first bit of ground, it was very poor conditions, so the hole wouldn't have stayed open by itself. So we had to install this casing in order to get to the good ground lower down the sandstone bedrock. Though the challenge that we had in our situation was that once we started putting in this casing, it got stuck about halfway, and then we couldn't take it out, or we couldn't carry on putting it in. So the challenge at that point was to determine how do we solve this problem, because we couldn't move the location of the gas pipe. We had to put the gas pipe where that casing was, half in and half out of the ground. So the solution that was eventually decided upon was to install another casing outside it, a pipe of 1.2 meters diameter, and slide it outside of the casing that was already in the ground with larger equipment, get it all the way down to the good rock down below, and then once we had that in, the friction forces on the other casing had been removed, so we could just take the other smaller one out, and we carried on then with our installation of our pipeline. In terms of the owner's engineers team on site, project management for us is a very important aspect of our job there, and the Carrington project was the first major CCGT project using ESB's project delivery model. The project delivery model is similar to the Project Management Institute techniques for project management. We have a multidisciplinary team involved in the project, including civil, mechanical, electrical, I&C, environmental engineers. A strong focus on quality. Our key aim was to ensure that our contractors delivered the plant of the highest quality, so that it was reliable and flexible for operation. A 3D model was developed for the entire plant to optimize layouts, to check for any clashes. There's hundreds of kilometers of piping systems and cabling routes throughout the entire plant, and the 3D model was used to ensure that there was no clashes between any of these systems that all needed to fit into the smallest area possible. And then also on top of that, you need to allow access for all your operators to get in there to operate different valves and different equipment. So the 3D model was excellent for walking through the plant before the plant had even been built. As with any project there has to be close management of the interfaces, and some of our key interfaces includes our national grid electricity supplier, our national grid gas supplier, and obviously our local community and local councils. We had a stakeholder management plan in place to ensure that each of those stakeholders was managed as best as possible. In terms of the lessons learned, ESB has built a number of these plants before. The last plant of this kind that ESB built would have been AHATA in the early 2000s, and there was a lot of lessons learned from that plant. So part of our project was to ensure that any improvements that were seen to be necessary or useful in AHATA, we implemented those in our plant here in Carrington. And also then, after we've implemented those, we can see there's further improvements that can take place for the next project maybe. So we're ensuring that we're passing on any lessons that we've learned from this project to our colleagues for their next projects. And obviously for our team, our biggest asset is our engineers, our people. We had an excellence through people system on site to support and promote the capabilities and experiences of our staff, especially our young staff that were based on site with us for the construction and commissioning. Just to zoom in a bit more on the project delivery model, as I said, like the PMI, every project is broken down into phases, and each phase is dealt with through an initiate, plan, execute and control, and a close stage. And then as we go through each of those phases, we consider all of the aspects as shown on the screen now. Just a bit more about the powertrain. The Carrington Power Station has two powertrains there. They can be viewed as two independent power stations, and on the video earlier you would have seen two stacks which are at the end of the main powertrains for the two of them. So we'll just zoom in here. The main part of it is the gas turbine here. So this is the main technology. You've got the air comes in here. We take filtered air from outside, and that filtered air runs through a compressor. So you've got compressed air running through here, and then once this compressed air comes out here, you've got two burners or two stages of burners, and you supply the gas at that point. So you've got air, you've got a fuel source, and you've got an ignition source through the flame. You have combustion at that point, and that combustion turns into mechanical energy by passing through the blades of the gas turbine here, and that in turn turns the shaft of the gas turbine. So you've turned your energy from potential energy to heat energy to mechanical energy, and then that is connected to the generator on the left hand side here to generate electricity. In terms of combined cycle, what we have on the screen at the moment is simple cycle, where you have a gas turbine generating electricity from a generator. I'll just show you a few photos here. That's just to put in context the size of the gas turbine. This is when it was placed on its plinth in one of the turbine halls when it arrived on site. It is similar to a gas turbine you would have hanging off the side of a commercial airliner, though obviously the size and scale of these ones are considerably larger. And just have a look at the generator. That's the rotor being installed in the generator on site. The rotor is about 140 ton. It's quite a precision activity, threading that through the generator to ensure you don't damage any of the parts. And then after the simple cycle, we've got the exhaust hot air from the gas turbine. So the exhaust air from the gas turbine comes out at about 612 degrees Celsius. So if you, in a simple cycle situation, that just gets released into the atmosphere and is lost. So in our combined cycle, we take that 612 degrees and convert that, use that energy to convert water into steam to drive a steam turbine in the system as well. So you see the hot air is running through the boiler here, and you've got all these different pipes hanging down that are full of water on the inside, basically a large heat exchanger to take as much of the heat out of the system, the exhaust, as possible to send it back into the steam turbine. That's just a photograph there of one of those pipe modules that we have inside the boiler in the way that it was delivered to the plant. That was delivered by barge. That would have required a special permit and an escort to bring that by road. After the steam has been generated in the boiler, it is sent by piping systems into the steam turbine. The steam runs through the blades in the steam turbine, turns the rotor again, and that same rotor is connected to the other side of the generator. So at this point, you have electricity being generated from mechanical force from both directions on your generator, from the gas turbine on one side and the steam turbine on the other side. Just one point of note there: when the gas turbine is started up, you do not have steam quality of sufficient to put into the steam turbine, so you have to operate in bypass mode until the steam quality reaches the required levels. So there's a clutch here which is disengaged for a bypass operation, so that you can generate electricity with your gas turbine and your steam turbines in bypass. Once you get your steam quality correct, you can engage your clutch, you send the steam into the steam turbine, and you're getting power from both directions. That's a photograph there of one of our engineers checking the blades on the LP steam turbine just before it was lifted into position on the center line of one of the units. In terms of safety in the plant, we have an excellent safety record on the site. On the right hand side there, you'll see we have a shared vision for safety, which was signed up to by all the key stakeholders in the project, and indeed every person that has been inducted on the site has signed up to that vision as well. In terms of ensuring the safest site possible, we've took a proactive approach to paying strong attention to the proactive indicators instead of looking at reactive indicators. Reactive indicators are LTIs, problems after they arise. Proactive indicators, identifying things before they actually become a problem. And throughout the project, our workers have identified 3,000 good catches on the site. Health and well-being has been nurtured on the site. We have a full-time medical centre in place with a site nurse and a paramedic. And throughout the duration of the project, 6 operatives that walked into the medical centre saying they were complaining of not feeling well or having chest pains, they were actually diagnosed with having serious heart conditions, and they all had stents applied or major surgery within days of that being diagnosed. So from our point of view, our medical centre has worked for that reason. The last 1.9 million hours of the project, which was the entire commissioning phase with the highest risks, was LTI free for us. And then finally then, what have we got at the end of it? We've got one of the most efficient plants in the UK. F-class plants is the type of gas turbine that is installed here. It's highly flexible to daily grid demands. The plant can ramp up at the fastest rate of any combined cycle gas plant in the UK at 28 megawatts per minute. So we can ramp up from about 220 megawatts to 440 megawatts for each unit in about 8 minutes. So we can supply additional electricity to nearly 500,000 homes in about 8 minutes if National Grid requires. We have a broader, stable environmental operating range, turn up, turn down ratio, which means that we can run at a lower level and still be emissions environmentally acceptable. We have the fastest shutdown rate of a plant in the UK compared to other CCGTs, and the plant is safe and easy to access for our operators. So all in all, it's providing reliable and stable generation for the UK market. Thank you very much.
Thanks, John. We'll kick off the Q&A session with, I think I was quite impressed with the use of the Manchester Canal to ship in a lot of the very heavy turbines.
Yep.
What did you make other use of the canal just for general, freight bringing in or excavation, or was it just for that specialist item you used?
It was for the main turbines and the generators. Those modules that we saw there for the piping came in as well. But also, as you can see in the photograph there, you've got these pipe racks running around the plant, obviously providing piping systems and cabling throughout the plant. They were actually prefabricated in Spain in very large sections. And we could only do that because we knew we could get them to the plant via the ship canal. They were too big to bring by road. Traditionally, you build it on site and bring it in on the back of a flatbed in pieces. We put that together in Spain, where we had better quality control, and then brought it to site on the barge.
When it's in operation, how many operatives have to be there?
The full operations team is of 43 people. And that includes daytime staff and all the shift staff. A shift staff contains three persons. So in the middle of the night tonight, there'll be 3 people operating the power plant. It's all run by computers. So you do not need many people to actually carry out major operations. So skeleton crew of 3 people to operate the plant.
Is there a point of stopping that pipe?
Pardon?
Is there a point of blocking the pipe?
No. The ground is it contained different materials, so there might have been larger rocks there than we expected, and that might have been what stopped it. But then once it stopped, it was the friction that was our problem to overcome. So I think it was very poor ground, and obviously a lesson learned is to try and determine more accurately what the ground conditions are like.
Did you have to bring a new bit to get around the existing 1.2 meter pipe, or how did you come around it to get the 1.4?
It was pushed in with rams from the outside, so it was jacked in.
On the risk side, say 10 years ago when the project was started, there was probably some sort of a risk register in the top 10 risks, or even just before construction. Was there a lot of that realised, or was a lot of it mitigated? Was there, say like that probably would have been unknown ground conditions, would have been big risks that would have been realised. Did you realise more than that? Was it a bigger one?
We did have a risk register, yes, and we kept the risk register up to date and had reviews of it on a very regular basis throughout the different stages of the project. And yes, ground conditions were a big risk for us. The example I had of the old piles from the old power station, that was one of our larger risks, and we mitigated that by managing the situation to design out the risk with the information we gave to our contractors. So there was obviously many risks involved in the project, but ground conditions would have been one of the major ones. Yes.
Was there any consideration given to the use of piles?
There was consideration, but because there was no information on the design of these piles or their integrity to last another 25 plus years, the easy decision was made to discount those piles completely and just cut them down 4 meters below our levels and just start again.
You
The-
mentioned that you determined the verticality of them. How did you do that?
We dug down a number of meters, exposed them so that we could see what direction they were going in.
Just extrapolated.
Yep.
We're done.
Okay. Thank you very much.
Thanks so much, John.
Thank you.
Well, hope you found it useful, and I'm sure the people in Manchester will be very happy to have their homes powered by this when it comes online. Well, they should be. So anyway, thanks. Our new program is published as well for the next year, so please pick up one, and this will be going out to our members anyway in the post in the next week or two. Our next event is at Battersea Power Station, end of October. We have a slight typo. It's about the Northern Line extension, which naturally will lead to a redevelopment of the Battersea Power Station area regardless. So look forward to that. That'll be up on our website in the next week or two. But otherwise, thanks for coming along tonight. If you want to stick around for a beverage or two, we'll head off to the Prince William Henry, which is just around the corner from here. But if not, I'll look forward to seeing you at the next event. So thanks for coming along, guys.